Hello and welcome to episode 6 of Astromagnet. I'm Arush Ramadurai,
And I'm Ishan Chakraborty.
and today we're talking to Avi Loeb, Frank B. Baird Jr. Professor of Science at Harvard University.
Welcome to the podcast, Professor Loeb.
Thank you for having me.
When did you first get interested in astrophysics? Why are you interested in astrophysics?
Well, when I was a child, I grew up on a farm and used to collect eggs every afternoon and used to drive a tractor to the hills of the village and read philosophy books. I wasn't very interested in science. And since I was born in Israel, I had to serve in the military. It's obligatory there. And I preferred to study physics because that was offered as an option rather than run in the field. And it was closer to philosophy for me. And then I established a project that ended up being funded by the US government, and that brought me to the US. And eventually I was offered a fellowship in astrophysics under the condition that I'll switch from what I was doing to astrophysics, to the study of the stars and other things in the sky. I didn't know anything about it. And then one thing led to another. Eventually, I became a professor at Harvard and the chair of the astronomy department for 9 years. And at that point, I realized that even though it was an arranged marriage, I wasn't planning to become a physicist, a scientist. Even though it was arranged by circumstances, I ended up being married to my true love, because in astrophysics, there are some deep philosophical questions that we can answer scientifically using the scientific method. For example, we can ask, what was there at the beginning? How did we come to exist? How did everything we see around us come to exist? What was there when the universe started? And another fundamental question, which used to belong to philosophy, is how did life start here on Earth, and are we alone? Are we the smartest kid on the block? I mean, you can be the smartest kid in Lexington High. Okay, that would be an accomplishment, but it doesn't mean much because, the half of the sun-like stars have a planet the size of the Earth, roughly the same separation. So you can imagine other civilizations around other stars. And so there are tens of billions of other planets like the Earth, just in the Milky Way galaxy, our own galaxy. And then there are 1 trillion galaxies like the Milky Way in the observable volume of the universe. So altogether, more planets like the Earth than there are grains of sand on all beaches on Earth. So even if you are the best student at Lexington High, and there are so many other schools in addition to Lexington High, let's imagine that you're the best student on Earth. That is not a great accomplishment because there are 10 to the power 20 other planets in the universe where you can have life like we have here, and where there might be better students than you are. And one thing I tell students in my class at Harvard is half of you are below the median. The median in statistics is exactly where half of the people are below. So for any class, half of the students are below the median. They get upset because all of them want to be the top 10%. But the point is, it's always true that half of the class is below the median. And, if I had to guess, I would say we as a civilization are probably somewhere in the middle of our class of intelligent civilizations.
Can you talk a little bit about the education that you received for your career and how that formed you as like a person and a scientist?
Yeah, so most importantly, I grew up on a farm, so I appreciated nature. I really enjoy nature. I jog every morning at 5 a.m. in the company of birds, ducks, wild turkeys, and bunnies. And, here in Lexington, nature is quite close to us and we can enjoy it. And that was something I got used to during my childhood. I appreciate more nature than people. I wasn't a social animal, so to speak, and I'm still not. So I don't have any account on social media, for example. I don't care how many likes I have on Twitter, because the truth about reality is not being shaped by what people think on Twitter. If you go 4 centuries back, there was a scientist called Galileo Galilei, and he said, it seems to me when I look through my telescope that actually the Earth is moving around the sun. And philosophers at the time thought the sun moves around the Earth. So they said, we don't want to look through a telescope. They put him in house arrest and they maintained their ignorance. But that didn't change the fact that the Earth moves around the sun. And we now know it for sure because we have space missions looking at the Earth from a distance. We can see the Earth moving around the sun. We know it for sure. The fact that those philosophers thought otherwise didn't change reality. So the point is, today, Galileo would have been canceled on social media because he was expressing a view that was not popular. But the beauty of doing science is you don't have to appeal to the popular view. You can rely on evidence that will guide you. And sometimes what people believe in is wrong.
Very interesting take on astronomy for sure. So your research covers a very broad range of topics. So we were wondering if you could talk about some of your research on gravitational microlensing in 1992. So like, what is microlensing and how did you propose to apply it?
Yeah, so Einstein, when he formulated this theory of gravity, predicted that light should bend near a massive object like the sun, for example. So in a way, light falls under the influence of gravity. It follows a trajectory which is not straight. And this is called gravitational lensing, that gravity itself can bend the trajectory of light. Just like a lens, if you have glasses or if you saw people with glasses, what the glass does is if it has a changing width, it changes the propagation direction of light and it can focus light on the eye. And that's why people wear glasses. So in much the same way, an object like the sun can bend light and through the force of gravity. And then if you imagine a planet near the star, a star like the sun, the planet can also influence the way that the light is bent. And what I did in 1992 was suggest that in fact, by monitoring the light from background stars, you can find situations where there is a foreground star in front of them that is bending their light because they get brighter when the light is focused. But the important thing is if they have a planet around them, like Jupiter, for example, that planet would affect the way that the light is focused, and you would see the signature of the planet as it moves close to the line of sight to the source. And that was my paper from 1992. We predicted that it's possible to find planets this way around very distant stars. We can't see the planets directly, but we can see their influence on the amount of light that we receive from the background star through the gravitational lensing effect. It's called microlensing because we are talking about very small lenses. In principle, you can get gravitational lensing by a whole galaxy like the Milky Way, and that is called gravitational lensing more broadly. So that was my work back when I started doing astrophysics. It was probably the most significant paper that I wrote early on. And by the way, I should say also that today this method is being used routinely to find the planets very far away.
So do you know like how many planets have been found using this method?
Oh, dozens of them. And we would never find those planets because they are so far away that you can't really see the light either emitted by them or reflected by them. The conventional method of finding planets is either from their influence on the star as they tug the star back and forth when they move around it, or if they pass in front of the star, you can see some diminution of the light coming from the star. They block a little bit of the light. That is called the transit. Or in principle, if they are close enough to us, you can see the light emitted or reflected by them. But these methods, all of them, do not work at very large distances because we just cannot detect enough light to be able to tell that there is a planet affecting the star around it. So microlensing, gravitational microlensing, is the only method to find planets across a distance comparable to the size of the Milky Way galaxy, thousands of light years away.
Would you be able to discuss the Sandage-Loeb test? So for context, what is the Lyman alpha forest and the acceleration of the universe that you were studying?
Right. So a lot of time has elapsed since the Big Bang. The universe started at a point in time, which we call the Big Bang, and we see it expanding since then. It was 13.8 billion years ago. And because this time is so long compared to our lifetime, you know, we live for only one part in a billion of that, you know, so it's really a very long time. We get the impression, the illusion, that nothing really changes in the universe when we look at it, most of it. I mean, there are some stars exploding that we can notice, but the expansion of the universe looks to us as if it's sort of frozen. We see a snapshot of it during our life. You know, if we observe the sky for decades, it doesn't change much on the scale of the universe. Okay, so that's the naive impression. But then about 20 years ago, I thought, well, actually, the universe is changing. You know, it's changing slowly. And the reason is, you know, as it's expanding, it's either speeding up or slowing down, depending on how far you look. And recently, the universe started speeding up its expansion. We call it the accelerated universe. So if you look at relatively nearby sources of light, you see, you're supposed to see that they're speeding up as you monitor them over time. If you look at very distant sources from where the light was emitted when the universe was very young, then you should see them slowing down. And the point is, can you see them? Can you see the movie rather than a snapshot of one image? And the answer is yes, if you measure very precisely the rate by which the universe expands. And so I wrote a paper saying, in principle, that is possible because there are, when we look at very bright sources like massive black holes that accrete a lot of gas onto them and shine very brightly, 100 times brighter than the entire galaxy that surrounds them. These are called quasars. We can see them all the way to the edge of the universe. So when you look at such a bright source of light, what you can see are clouds of gas along the line of sight to that source that absorb the light. And you can tell where they are along the line of sight. They expand relative to us at different speeds, depending on how far away they are. And so you can tell those clouds, they are called the Lyman alpha forest. They are called a forest because each of them produces an absorption feature in the light coming from the quasars. So you can sort of see a sequence of absorption features which look like trees. So it's called the Lyman alpha forest. Lyman alpha is the transition of hydrogen, which is the most common element in the universe. So we are basically seeing hydrogen clouds absorbing the light from the quasar at different distances from us. And they, in principle, they would change their speed relative to us if you monitor them over long enough time. So I calculated that over a decade, you might actually notice the fact that they are not moving away from us at exactly the same speed. And so that was my suggestion. And turned out after I published my paper that an astronomer on the year that I was born, and another astronomer discussed that in the context of the expansion speeds of galaxies. It's Alan Sandage. So the effect is called, after the two of us, the Sandage-Loeb test of the expansion of the universe. And the basic point is we can see the universe changing in time. We can take a video of the expansion of the universe, not just a snapshot.
And was that test, has that test been carried out?
Not yet, because it's very challenging to develop a spectrograph that would be sensitive enough to see this slight change in the expansion speed of those clouds of gas that I was describing, but it's something on the to-do list of the next generation of telescopes. So during your lifetime, my hope is that we would actually see evidence for the fact that the universe is not just expanding, but its expansion is changing in time. And by the way, I should say on that note that I also wrote a paper shortly after that, forecasting what will happen in the future. And we know the universe is not just expanding, but accelerating its expansion. So if you imagine a galaxy far away from us, it's moving away from us faster and faster as time goes on, and eventually it will exceed the speed of light, and we won't be able to see it anymore, and we will be left in the dark. And so it so happens that the future of the universe is quite gloomy. You know, we will be surrounded with darkness around us, and no other galaxy except for ours will be visible to us.
Sounds very exciting to have that happen in our lifetime. The Sandage-Loeb test, not the getting dark part. But
No, there is plenty of time. I think you should worry mostly about what humans are doing to the Earth, because currently all our eggs are in one basket here on Earth, and I recently wrote an essay in Scientific American, and I classified intelligent civilizations, and I said that our civilization is class D. It gets a grade D because not only that we are not adapting well to the conditions around us, but we are actually making them worse. So we are changing the climate without taking care of it, and it will make your generation cope with challenges that my generation did not. And so a class C civilization would be that that takes advantage of whatever nature gave it, and not destroying it. Okay, so we are not as good as that. And then you can imagine class B civilization, which doesn't really depend on its host star. It doesn't care about whether it's next to a star like the sun. It doesn't need the sun to be warm. It can build a platform in space that keeps it warm, for example, using nuclear energy or some other energy source, and it doesn't rely on the star. So that's class B civilization. And then you can imagine the most advanced civilization possible, and that is the one that can recreate the astrophysical conditions around it. For example, you can imagine a civilization that creates a baby universe in the laboratory. So creating the entire universe in the laboratory. So if you want to read more about it, check out my Scientific American article.
will do. You also researched the collision of the Milky Way and Andromeda galaxy. So could you discuss a little more about that as well?
Yeah, so apparently there is a galaxy just like the Milky Way called Andromeda. It's our sister galaxy close to us. And it turns out that it's approaching us on a collision course. And it will take a few billion years before it will collide with the Milky Way. So the night sky will change. The Milky Way galaxy looks like a strip of stars in the sky. And the reason is because it's a disk galaxy. It looks like a plate. And we are looking at it edge on. Just think about looking at a plate edge on. It looks like sort of a strip, a line. And that's what the Milky Way looks like, a line of stars in the sky. It's called the Milky Way for that reason. But once we collide with the Andromeda galaxy, the Andromeda galaxy looks just like the Milky Way. It's a disk galaxy. And once the two galaxies will merge, all the stars will be scrambled. And then you will end up with a system that looks like a football, ellipsoidal. And the sun will be moved away from where it is right now. So I was wondering about the collision with Andromeda and how the night sky will change. And in about 15 years ago, I convinced a colleague of mine, a postdoctoral fellow, to actually simulate that. And we wrote the first paper forecasting what will happen a few billion years from now. And this is probably the only paper of mine that has a chance of being quoted a billion years from now. All the other papers will be forgotten. Maybe this one will be remembered.
In your recent book, Extraterrestrial, you stated that the interstellar object Oumuamua could have been created by terrestrial life. Discuss Oumuamua and what evidence led you to this conclusion?
Right. So this is the first object that was discovered near Earth from outside the solar system. And we knew that it's not bound to the sun because it moved too fast. And astronomers initially, I mean, it was discovered by a telescope called Pan-STARRS in Hawaii. And Oumuamua means a scout in the Hawaiian language. At first, astronomers assumed that it must be a comet, but then it turned out that there is no gas or dust in a cometary tail around it. We didn't detect anything. And so it was definitely not a comet of the type that we have seen. And a comet is just a rock that is covered with ice that gets evaporated when it gets close to the sun. There was nothing of that type around this object. And so the thought was that maybe it's a rock, a bare rock without any ice on it. No icing on the cake, so to speak. But as the object was tumbling every 8 hours, the amount of sunlight reflected from it changed by a factor of 10. And that meant a very extreme shape. And the best fit to the variation of light was that of a pancake, a disc-shaped object, which is very unusual. And then the object exhibited an excess push away from the sun by reflecting sunlight. And the only way I could explain it is if that push comes from reflecting sunlight, because there was no evaporation, no cometary tail, no rocket effect acting on it. And then in September 2020, just a year ago, there was another object that exhibited similar qualities. It was given the name 2020 SO, and it was pushed away from the sun by reflecting sunlight, no cometary tail, and it ended up being a rocket booster that we launched in 1966. That demonstrates two things. One, that you can tell if an object is artificial or natural, because we know that we produced this rocket booster. So the question is, who produced Oumuamua? And the second point is, the object needs to be very thin in order for sunlight to push it. So, but it doesn't necessarily need to be a sail, you know, like a light sail. It could be thin for a different purpose. In the case of the rocket booster, these were just thin walls that it had. So without a good image of Oumuamua, we don't know what its purpose was. And of course, you know, a picture is worth 1,000 words. In my case, a picture is worth 66,000 words, the number of words in my book. To write the book, if I had an image of Oumuamua, and my hope is that we will get such an image in the future of an object similar to it. And that is the purpose of a new project that I established in July 2021 that is called the Galileo Project. We want to find more objects that look like Oumuamua, do not look like a comet or an asteroid, and we want to figure out nature, because if they are artificial, they may tell us that there is another civilization out there. Maybe they are smarter than we are, and we can learn from them.
So do we know where Oumuamua is now?
Yeah, it's far away. It's 1,000,000 times fainter than when it was close to us. So we can't really see it. We can estimate at what distance it is, but we can't observe it. And so instead of obsessing with an object that we can't see anymore, we should find more of the same. You know, when you go to the kitchen, you find an ant walk on the floor, you get alarmed because you realize there must be a lot of ants that you're not seeing around. And the same is true for an object like Oumuamua. There should be many more that we could find by surveying the sky in future years. And that's what the Galileo Project aims to do.
So it's a matter of waiting for the next one. then.
Yes, and if we catch it early enough, we could send a camera on a small spacecraft that will take a close-up photograph and maybe even land on it. Because the analogy I make is with a caveman finding a cell phone. And the caveman who is used to playing with rocks would argue that the cell phone is just a rock of a type that we've never seen before. So a lot of my colleagues were saying Oumuamua is a rock of a type that we've never seen before. For example, an iceberg of frozen hydrogen, or an iceberg of frozen nitrogen, things that we've never seen before. They wanted to explain the properties, the unusual properties of Oumuamua. And that's similar to the caveman saying, oh, this cell phone is just a shiny rock of a type that I've never seen before. Now, if the caveman would throw away the cell phone, then that would be the end of it. If we don't try to collect more data on other objects similar to Oumuamua, we will never figure out that they're artificial. But if the caveman looks at the cell phone and presses a button and realizes that it records his voice, presses another button and realizes that it records his image, then it will become clear that it's not a rock, it's something else. And what I want really is for us to land on an object that looks weird and press some buttons.
So you want to like physically land on one of them?
Yeah, because there was actually a mission called OSIRIS-REx that landed on the asteroid Bennu. And if you look at the photograph that was taken, it does look like a rock. It has a lot of small fragments on it. And this mission, the OSIRIS-REx, took a sample of that rock and will bring it back to Earth in 2023. So it's possible to land on such an object. And of course, if such an object happens to impact the Earth, it will become a meteor, and we can, in principle, put our hands on it if it hits the ground. So we should also look nearby, and that's the second part of the Galileo project, to look at objects that are closer to us. And on June 25th, there was a report delivered by the Office of the Director of National Intelligence to the US Congress, saying that there are objects whose nature is clear. Military personnel saw such objects in the sky, and they don't seem to behave as technological equipment that humans produced. So that's very intriguing. What are these unidentified aerial phenomena? And actually, on November 10th, I will be attending a panel discussion in the National Cathedral in Washington, D.C. at 7 p.m. With the head of NASA and the director of the Office of National Intelligence and the theologian. And it should be very interesting. If you are interested, you should register to watch it online. So the Galileo Project, I should just say, the Galileo Project aims to build telescope systems that will try to identify the nature of these unidentified aerial phenomena by using an optical telescope, an infrared sensor, radio instruments. And we are currently developing the first such telescope system that we will put on the roof of the Center for Astrophysics at Harvard. I was just a few minutes ago, we were just discussing the instruments we are purchasing and how we want to put them together by spring 2022. So stay tuned. Once we have a working telescope system, we will put it in a remote location, try to record what we see in the sky and whether we notice any identified aerial phenomena. These telescope systems will have fisheye lenses that they can look at the entire sky all the time. And then we will build the copies of that system. And all of this, the Galileo project, became possible as a result of generous donations of a few individuals that came to the porch of my home here in Lexington and offered the financial support for this project. And that allowed me to assemble a team of other 80 scientists that are engaged in this project.
Very cool. So you've written, around 800 papers, and you've studied lots of fields of astrophysics. So of all the research you've conducted, do any of the projects stand out as the most rewarding thing you've done?
Oh, it's actually what I'm doing now, in the sense of trying to figure out if we are alone, or is there a smart kid on the cosmic block, because that will change everything for humanity. Just imagine that there is another technological civilization out there, and that we detect equipment that they sent into space. Just imagine how it will affect everyone, and it will change our aspirations for space. It will affect religious, philosophical beliefs about our place in the universe. It will bring in the question of how we want to behave, given that we now know there is a smarter kid on our block. And my hope is, I'm an optimist. My hope is that it will inspire us to behave better, because if you look at human history, you find that it was shaped by the desire of people to feel superior relative to each other. For the best example is the Second World War, where the Nazi regime triggered the death of 75 million people. That was 3% of the world population in 1940. It's 20 times more than the number of deaths caused by COVID-19, okay? And all of that was because a group of people decided to feel superior relative to other people. And the point is, if we find another civilization far more advanced than we are, all of our genetic differences become meaningless. We should all treat each other with respect as equal members of the human species.
So do you have any advice for students, like high school students, college students, trying to enter your field?
Yeah, so the way I see science is as a privilege of maintaining your childhood curiosity. And if you're curious about the world, my advice is stay curious, because when I was your age, what I remember is going to a dinner and asking a difficult question, and all the adults in the room would pretend that they know the answer to this difficult question. And it was obvious to me that they don't really know the answer. They are just pretending that they know the answer. And that was the good situation, actually. The worst situation was when the adults in the room would simply dismiss the question and say, it's not important. Forget about it. And then they would move to another subject that is of more interest to them, where they can demonstrate that they are knowledgeable. And the problem is that as you grow up, you lose your sense of curiosity, because you don't want to appear as if you're asking questions that people ridicule or dismiss, and you want to maintain a respectable image. And then you lose your curiosity. You're not willing to take risks. You're not willing to ask difficult questions that are the most exciting ones. And the reason that I enjoy doing science is because I think it's a privilege. If you are a scientist, you can ask those difficult questions and try to address them. And my advice is, don't listen to the adults in the room. If you are curious, stay curious throughout your life. Become a scientist and answer these questions. Many times the adults in the room are just pretending to know much more than they actually do.
Is it all right if interested high school students contacted you for advice or guidance via email?
Oh yeah, that would be great. I very much like to communicate with young people, because they are not so attached themselves as adults are. Adults are driven by their ego very often. And moreover, they don't have a baggage of prejudice. Young people are open-minded. They're willing to explore the unknown, which is pretty much the way I feel. I haven't changed much since I was a kid your age. And I see that as a great a privilege as a scientist to be able to stay that way. And I really enjoy interacting with young people, working with young people. So definitely feel free to contact me.
Thank you. So we had a very good time interviewing you, hearing about your work, your insights on it. So thank you for appearing. And so that was Avi Loeb. And to learn more about his field, check out additional resources on our website.
And I should also say that my daughter is in Lexington High.
I think I know your daughter, yeah.
Okay.
Yeah.
So, yeah, I'm very proud of her.
Thank you very much. And we'll be back with another episode. Yeah.
Thank you. Bye-bye.